Hello guys, welcome to our another online class. So in this topic, we're going to discuss about forces, a free body diagram. So before that, we need to review what is force. Force can cause an object with mass change its velocity to accelerate, and force has a formula which is equal to mass times acceleration, or it's just F equals to ma. Okay, so this is the symbol for the formula, and can also be described as intuitively push or pull, and has both magnitude and direction, making the force as vector quantity. And the unit is newtons, or just N, or kilogram meter per second. Okay, so mass is should be in kilogram, and acceleration is meter per second squared. Newton's first law. This law is very important because without this law, we cannot understand what is a free body diagram. So, as states that an object will remain at rest or continue to move with constant velocity unless acted upon by a resultant external force. So again, if the object is at rest, it will not move if there is no external force applied. Also, an object will continue to move. This is not possible on Earth because there are a lot of external forces that makes this um, object object to stop. It's like air resistance, and also friction, everything like that. This is only possible in space because in space there is no resistance at all. So as our satellite, like the Voyager 1 and 2, traveling outside the solar system at this moment, and there is no external force that is stopping them. Forces in equilibrium. From the word itself, equilibrium meaning equal. So a pair of equal and opposite forces acting on the body would not affect its motion. So meaning the push and pull on a particular object is at the same magnitude. So that thing wouldn't move, which applies our Newton's first law. And the resultant forces is zero. So suppose you have a push there with a particular amount of magnitude and a force also here. So force 1 and force 2. So there would be no resultant force if these two are equal. Okay. One thing to understand the forces is by drawing the free body diagram, or we can say it as free body force diagram. Usually the force is omitted, we just actually call it free body diagram. So a pair of equal and opposite forces acting on the body would not affect its motion, making its forces in equilibrium. So the application of the Newton's first law. And by the way, Newton's first law is also called law of inertia. Okay, so let's say we have this diagram, and we have the object here. This is our object. And if this object is just sitting on the ground, there would be a weight, or the force of gravity. Force of gravity is the weight, and the opposite of force of gravity is the force normal. Otherwise, if you're just standing on the earth, then we'll go towards down the core if there would be no normal force, the one that is acting opposite to our weight. And acceleration, there would be opposite for that is friction. So suppose we have a climber. As you can see, he is holding a rope, and there would be tension for this. We have a T, a tension, and of course this man has a weight which is W, and there is a normal force acting on his feet going up. So there would be something like that. So if we just look at the diagram, the free body diagram, it has a tension here, it has a normal force, and of course we have weight. To calculate the amount of forces on the tension or the T and on the normal force, we need the angle of each inclination towards the vertical or the horizontal. Okay, can be either here or here. It depends actually. It's either in a vertical or in the horizontal ground. Compute the tension and the normal force. So first we need to calculate the forces in equilibrium. So meaning both um, forces up and forces down, or forces left and right, should be equal. Otherwise, there would be no equilibrium for this. Okay. So vertical plane. The vertical plane we're talking about is this one, the vertical plane. The opposite of this vertical here in this side at the top is your weight. Okay. So it's just straight line. There's no need to change for that. Applying our trigonometric functions to get our vertical plane for the value of P and the value of T, we need to use cosine, because as you can see, this is our angle here. If we see it in some perspective, you can actually lift this one over for this one or in this one. So we are actually finding for the adjacent of both P and T. So the adjacent is just cosine formula. Okay, to get that, so for P, we will have cosine theta. So if it's cosine theta, we'll have adjacent, which is the ones that we're going to find. Adjacent, the x over the hypotenuse. Our hypotenuse here is P. Okay, and also in the other side, cosine theta, so this is theta 1 here and this is theta 2, is equals to the x, or the value here, over the hypotenuse, which is the T. Okay, so our axis or our vertical plane is this axis. So if you're going to rewrite this equation, this will be just P cosine theta 1, same on the other side, T cosine theta 2. So we have here P cosine theta 1 plus T cosine theta 2, because there are two forces here for the value of P and for the value of T. That's why there is 2 minus the weight, because the opposite of the values that we have solved here is the weight, our weight here. So weight is actually here. This one equals the weight, and we transfer that to this side. That's why it becomes negative. which is equals to 0 because we have transferred the value here, no value on this side. So next, finding the horizontal plane. So same thing, applying our trigonometric function. This time we're going to use the opposite side. The opposite side is this one, which is the sine. So again, our values for the angle is here, this one, here and here. We need the horizontal, which is this side, or it's actually the same as this side if you're just going to transfer here, same as here. Okay, this direction is opposite, or this is just the component of your P and T. So the direction is opposite to each other, going to the right and going to the left. For this one, we're going to use the sine function. So sine theta 1 equals to opposite, which is our x, divided by the hypotenuse, which is your p. So same thing on the other side, sine theta 2 equals to x divided by t. So rewriting the equation, we will have p sine theta 1. Okay, so this is the force value for this opposite side going to the left. And same thing on the other side, t sine theta 2 for this value. Okay, so then we'll have this formula. So this is equated to 0. The same thing on what we have done on the vertical line. We actually just transferred one of these equation to the other side because both of them are actually equal. So t sine theta 1 equals to t sine theta 2. And if you transfer one of them to the other side, one will become negative. Okay. So example, a 10 kilogram mass is suspended from a beam using a length rope. The mass is pulled to one side so that the rope makes an angle of 40 degrees to the vertical. Okay, we have our free body diagram here. So first thing you really need to do is draw the free body diagram, which is this one. So the rope is suspended to the wall. There is a horizontal force that is pulling it, which is this F, and we have the inclination of the rope, and we'll have the tension, and it makes a 40 degrees angle. And of course, this object will have a weight, which is equals to mass times the gravity. Okay, so we'll just put our free body diagram here. Then first solve for the vertical and horizontal plane. So first, calculate for the vertical plane. Vertical plane using our uh, trigonometric functions again. So the vertical plane is this one. Take note. Cosine 40 degrees equals to the vertical component divided by t, or this is just equal to t cosine 40 degrees. So that is the force. Take note, this is the force for this one, for the vertical component. And the opposite for the this force is just the weight. So therefore, we'll have the formula just as that. Okay, so we have t cosine 40, and the opposite is just the weight, mass times gravity. Okay, then Substituting our value, we have mass equals to 10 kilograms, and of course gravity is 9.81. Then transposing our equation and just leave t. So this one we transfer it on the denominator, then we compute using our calculator. Then our final answer for the force of T is 128.06 Newton. Okay, so the next one, we need to find force. We already found the tension, which is the T. We need to find the force. So force is already on the horizontal plane. It's already straight on the horizontal, so there's no need to find its component like in our tension here. So we just need to find the opposite force of this tension. Okay, so if you have inclined tension, the components will either be this one, the horizontal, and the vertical. So it should follow the direction of these forces. Okay, so finding the horizontal component for our t, we use sine because that is opposite with our angle. So sine 40 equals to the horizontal component divided by the tension. So that is just t sine 40. Okay, and the opposite for that is just f. So that's just easy. So horizontal plane, f equals to t sine 40. Then we already have the value for t. It will be just substituting directly for our t times sine 40. Then the force for that is equals to 82.32 newtons. Okay, so I hope you understand our discussion about free-body diagram, and if you have any suggestion, you can just leave a comment below, and I hope you have a great day.